Mr. V's Biology.
Science rules.
Mr. V's Biology.
So we are going to do some enzyme practice today. And so we are in the Unit 2 Biochemistry packet on the enzyme practice page. So number one, the enzyme would most likely affect reactions involving which of these molecules. So if I look at the enzyme, I can see that the active site looks like this. So I know that the answer is going to be substrate letter C only. Awesome. Number two, which graph, A or B, shows the amount of substrate going to zero faster? And that would be A. So the substrate goes to zero faster here than in B. If both graphs A and B show the rate of an enzyme, which enzyme is more effective? Well, that would be enzyme A because it takes all the substrate and turns it to a product faster than enzyme B. Number four, what variables affect enzyme activity in each of the graphs? So if I look at the graphs, I know it's temperature. Temperature affects enzymes. pH affects enzymes. Remember, if the pH or the temperature changes too much, the enzyme becomes denatured and doesn't work as well. And the third one here is substrate concentration, how much substrate there is. Number five, what is the optimal condition for each enzyme represented by the graphs? The optimal condition is when the enzyme would work the best. So for temperature, if I look at the top of the graph and go down, I would say around 37 degrees. 37 degrees Celsius is the optimal temperature for this enzyme. If I go to pH, go down, probably about 7.8. And letter C, what's the optimal substrate concentration? We're going to skip that because it's not really on there. Number six, explain what happens when hypothermia sets in, when enzymes get too cold. So I know, for some reason we got lots of jumping around with this page. Explains what happens when hypothermia sets in, when the enzymes get too cold. The enzymes become denatured if the temperature changes drastically. Same thing with a fever. So the opposite way as well. If you get a fever, same thing's going to happen. Enzyme becomes denatured and they won't work as well, which is why you don't feel well. Does the same thing happen when enzymes get too hot? Why or why not? Yes. Explain why graph C levels off. Use enzymes and substrate in your explanation. Why doesn't it matter if enzymes keep getting added? So my enzyme activity goes up and up and up and up, but saturation, substrate concentration, meaning if there is the same amount of substrate and enzymes, it can't go any faster. It's going to be at the max, which is why this graph goes up and then levels off, is because there's the same amount of enzymes and substrate. Number nine, what can affect the speed of an enzyme? Well, we set them: temperature, pH, and how much substrate there is. And number 10, describe the difference between the relationship between the enzyme concentration and reaction rate. Well, if you look at this, enzyme concentration and reaction rate, as there's more enzymes, the rate of the reaction can go faster. That makes sense. If there's more enzymes, the reaction can go much faster. All right, and let's look at 35. Propose an explanation for this relationship. Well, we just said more enzymes make the reaction go faster. Okay, what would cause the rate to level off? Well, it would stop going up if no more enzymes were added. All right, so now I have two enzymes, pepsin and trypsin. Now, usually enzymes end in ase, but the original enzymes that were ever discovered and studied don't follow that rule. So what is the optimal pH for both of these enzymes? Pepsin. So if I look at pepsin and go down, I would say 3, pH of 3. And what is the optimal pH for trypsin? If I go to trypsin and go down, let's say pH of 8.2. Number 14, predict the reactivity of trypsin at a pH of 14. So if we just said the optimal pH for trypsin is 8.2, if I look at 14, I know that trypsin will become denatured and not work. When do neither enzyme work? Neither enzyme works at a pH of 12. Compare the rate of pepsin catalyzed reaction at a pH of 3 with the rate of trypsin catalyzed at a reaction of 3. So if I look at 3, that is like the best for pepsin, but it is too acidic for trypsin, which makes sense. If I look at what these do, pepsin digests protein in the stomach, where trypsin digests protein in the intestine. So it's more acidic in your stomach than it is in your intestine. At what pH values is pepsin likely to be denatured? Well, above or below a pH of 3, because that is the optimal pH for that enzyme. What can you infer about the pH of a stomach and an intestine? A stomach is more acidic than the intestine. So now we're going to make sure we go over everything that we've learned so far in biochemistry. So the blank and blank are always in the center of an atom. So in the center of an atom, we have the protons and the neutrons. Scientists call the center of an atom the nucleus. The electrons are always found whizzing around the center in the area called the electron cloud. The most common elements in living things are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. I can remember that by remembering CHNOPS, CHNOPS, CHNOPS. Using your periodic table, calculate the number of protons, neutrons, electrons, and valence electrons found in the following elements. So it looks like if I go to just type in periodic table, I can bring one into my review here. Not that one, of course, because it's blurry. Okay. Perfect. So how many protons are in carbon? Well, it's got an atomic number of 6. So I know that there are 6 protons and 6 electrons. The mass is 12. So to find the neutrons, 12 minus 6 is 6. Hydrogen is the number 1. So it's got 1 proton, 1 electron. It's got a mass of 1. So 1 minus 1 is 0. Oxygen, 8 and 8. It's got a mass of 16. So 16 minus 8 is 8. Nitrogen has a mass of 14 with an atomic number of 7. That means they're all going to be 7. And phosphorus, 31 and 15. So that means that there are 15 protons, 15 electrons, 16, or 31 minus 15 is 16. We're going to skip the number of valence electrons. Number 4, ionic bonding occurs between a non-metal and a metal. Covalent is a non-metal and a non-metal. Hexagons below represent molecules of glucose, a type of monomer. Draw the polymer starch would look like after polymerization of the monomers. So this is from the cracker demo. I have those monomers, those monosaccharides. I need to bond them. So I take sugar and I bond them, and now I have starch, like what's in a potato. Molecules like the polymer of starch you have just drawn are also called, well, if a monosaccharide is 1 sugar, I have a bunch of sugars there, so that's called a polysaccharide.